Hi, in this video we will present our EE599 project, Object Transfiguration with GANs. Object transfiguration is one of the challenging subtopics in the image translation area. Its main objective is to change the object in the image from one domain to another domain, like change the dog to the cat. From our motivation, our object transfiguration task have three difficulties. First, we want to incorporate texture and color transformation, as well as the shape deformation in our task. So, our model can perform the task when two object domains have obvious shape difference, like cat and dog. Second, we use unpaired data in our task. The third difficulty is that we will perform this task without help from the other additional information. For example, the segmentation masks. Our baseline model is GAN-EMORPH, which adopts the cycle pipeline as used in the cycleGAN. The main contribution of it is to use the dilated convolution in the discriminator and treat the discrimination to be a semantic segmentation task. The output of discriminator is now a map of real or fake values. And based on this map, the generator can be told to focus more on those regions seem unrealistic. Two important loss functions are added onto this model, the feature matching loss and the SSIM loss. The SSIM loss is used to preserve the structure of the reconstructed image, and the feature matching loss is used to force the generated image and real image from the same domain to have close features extracted from the discriminator. However, we can see that no loss function is added to regularize the real image and the generated image in this model. So, this model cannot well preserve the object information from the real image. To well preserve this information, we replace the feature matching loss with two loss functions, spatial perceptual loss and the style perceptual loss. Perceptual loss is a special type of loss built from deeply extracted feature maps from the neural network. In our model, we use a discriminator to extract these features. Spatial matching loss is used to regularize the spatial information of the object. It's based on the L1 norm difference between feature map in a deep layer of two images. Because the deep layer feature maps only contain spatial information of the objects, as shown in this figure. Style matching loss is used to regularize the stylistic information of the object, like shape and structures. It's based on the L1 norm difference between the gram matrix of the feature map of two images. This matrix does not contain spatial information, but contains information of shape and structure. Also, as we move in deeper, larger scale structures are mainly preserved as shown in this figure. In our model, we add the spatial matching loss between the original image and the generated image to make the generated object have similar spatial information to the original object, like the location and the pose. We also add the style matching loss between the generated and real images to make the generated object reproduces similar stylistic features of the real object, like the shape and structure.
Next, let me introduce our implementation. This two plot shows the architecture of the generator and the discriminator. The blue block stands for the convolutional layer, the green block stands for the residual block, the orange block stands for the deconvolutional layer. The yellow block in the discriminator stands for the dilated convolution layer. When we construct the feature matching loss, the output of the last dilated convolution layer is compared. The style loss compares all of the three outputs of the dilated convolution layer. Next, let me introduce our dataset. Our dataset is about cat and dog. The number of each category is listed here. Before each image is fed into the network, they are resized to 128 by 128. And we also augment the training set by random rotation, random translation, as well as horizontal flipping. Here are also some important hyperparameters. As mentioned just now, in our project, there are several lossless functions. We must use some ways to combine them together to form a final loss function, which is shown below. We also normalize each loss function by their moving average to make the selection easier. We train our network for 40 epochs. In each epoch, we update our network for 1000 steps. We compared our model with GANimorph. Here are some results of GANimorph. The left image is the input image, and the right image is the generated one. From the first row, we could say that GANimorph could not preserve the location information, especially from the first image. The face of the husky lies in the center of the image, but the generated cat does not. From the second row, we could say that GANimorph could not preserve the posture and orientation information. For example, in the first image, the dog is kind of looking to the right, but the generated cat is kind of looking to the left. From the third row, we could say that GANimorph has the diversity of GANimorph is not so good. Even if the input image is very different, the output image are all summarized with the same expression. Our results shown here. From the first row, the location of the input image is well preserved. Especially from the second image, the face of the husky does not lie in the center of the image, and the generated one is similar. From the second row, we could say the posture and the orientation is preserved well, and the third row shows the diversity of our model. We could not only generate husky, but also summarize with different expressions. We also do some ablation study to further explore the functionality of each loss function. In the first setting, the style loss is dropped. From the output images, we could see the face is wired. For example, the nose of the cat generated by the first image does not lie in the center of the face. So, the style loss could keep detailed information like relative location between nose and eyes. In the second setting, the feature matching loss is dropped. The location of the generated face is not preserved. For example, in the third image, the face of the generated cat is totally uncorrelated with the input dog, and the orientation of the second face is also different. So, the feature matching loss could preserve the spatial information such as location and posture. In the third setting, the SSM loss is dropped. We could hardly recognize a face from the output images. So, the SSM loss could help to preserve the basic structure of a face. That's all of our product. Thanks for watching this video. Thank you.